All right, I'm going to go ahead and get started. I'm Iris Tien. I'm from the School of Civil and Environmental Engineering at Georgia Tech. And I'm going to talk about the project that we have on mapping infrastructure interdependencies for improved emergency management and resilience investment decisions. So I wanted to give a bit of an outline of what I'll talk about today. So I'll start with our research objective, which is first, as the title suggests, mapping critical infrastructure interdependencies with the overall objective to enable municipalities to better understand their vulnerabilities. So we're really looking at cities here to be able to make informed decisions based off of more comprehensive risk assessments. I'll talk about our technical approach and research methodology. It really involves a close collaboration with the City of Atlanta. So Georgia Tech is right in Midtown Atlanta. So we really wanted to kind of get out of the lab and really interact with end user stakeholders. So I'll talk about that collaboration. And the focus of the project in this current phase is on emergency management, including critical water services and potential vulnerabilities to cyber attack. I'll talk about our outputs and deliverables. The first is a tested interdependent system model. And then the beginning and some initial results on the set of risk assessments that we've been able to perform using this tested model. I'll talk about some of our target end user customers. So this is really people within the city, so it includes the Office of Emergency Preparedness, the Department of Watershed Management, and Atlanta Information Management. And then I'll talk about the benefits to these end users, both by specific end users and also by the specific deliverables that we're looking at. All right, so to talk a little bit in more detail about our research objectives. So there's three main objectives that we have in this project. The first is to identify and map the points of contact between infrastructures. So this is really to better understand how these systems behave. So traditionally, each of these individual systems have been managed within individual silos. And so this is trying to have a more comprehensive and holistic understanding of how these systems interact. The second is to build and test a model of interdependent infrastructure systems. And so this is both building the model, but then also testing it and validating it with real data. So to kind of go from theory to real world applications. And then to be able to perform these more comprehensive quantitative risk analyses that incorporate interdependencies to consider vulnerabilities beyond single systems. And the third main research objective is to really break down silos in municipalities across infrastructure stakeholders. So that was something that we really set out to do at the beginning of this project, is to kind of make these different entities and these critical infrastructure stakeholders talk to each other and kind of understand how their systems connect and interact. And then also to integrate the analyses from kind of part two of this project into city risk assessments to improve emergency management and inform resilience investment decisions. And then overall, the idea, kind of large picture idea, is to decrease system vulnerabilities, decrease chance of cascading failures, and increase resilience of our infrastructure. So now I'm going to talk in more detail about our technical approach. So I'm going to start with looking at our end users first. I think it's really important to think about where this research is going to go, who's going to be using it. And so what we're really focusing on is municipalities. And so related to that, this project involves a close collaboration with City of Atlanta across critical infrastructure stakeholders. So starting with Georgia Tech and me in the School of Civil and Environmental Engineering, working very closely with the City of Atlanta Office of Emergency Preparedness and the Director of Emergency Preparedness there. And then the Department of Watershed Management. So this is looking at kind of critical water services for emergency services. And then the information and information security element of it is through Atlanta Information Management, which they abbreviate as AIM, and also the Office of Information Security. And so this is kind of the team that we're working with for the project. And then in terms of the technical approach for this, the specific focus that we have in this phase one of this project is on emergency management. As I said earlier, critical water services and potential vulnerabilities of cyber attacks. So we're looking at the water system, how it is needed for emergency services, and then potential cyber attack on that water system. And so in order to study this, we have a pretty stepped out research methodology that we're looking at, which I've shown here. And what I'm going to do in the next few slides is I'm going to go through each of these steps, talk about what we did, and then show some results from each of these individual steps. So I'll start from 1A to 1B, 2A to 2B, 3A to 3B. So to talk more about 1A here, so identify and map critical infrastructure points of contact. So we're looking specifically right now at dependencies between water and power. So as we know, a lot of water functionality depends on power systems. So on the left here we have the City of Atlanta water distribution network. The water pipes are shown in red. We have terminal distribution nodes, and then the circles are individual pump stations, triangles treatment plants. The squares are SCADA control. And the threat scenario that we're thinking about is a cyber attack on the power grid resulting in loss of service for the water network. The idea here is that we want to see where the individual points of connection are between these multiple infrastructures. So whereas the water system, for example, traditionally has just operated with just the water system, but now as we introduce additional more advanced controls, then we introduce dependencies with power, dependencies with communications, with fiber, with cell, and power as well. So once we've identified and mapped these points, then we want to build our interdependent system model. So this is going to be step 1B. And so the framework that we're using is a Bayesian network framework. So this is a probabilistic graphical model where I've shown a simple example here. We have different nodes. Each of these individual nodes can be individual different components of the network. Those links or those arrows between the nodes represent their dependencies. And so this is, first of all, is probabilistic, so we can capture risk, uncertainty, so we can say if we're not sure how things are going to behave, if we have these hazards or threats that are uncertain, we can incorporate those probabilities in there. And then with the different dependencies that we can model connections both within a single system, and then we can also model connections across systems. And so we wanted to specifically, for this project, model interdependencies. So this is building off of some work that we have done and then also expanding it for this particular case. We're looking at two specific types of interdependencies. The first is what we call service provision interdependency. So this is when one component depends on the service outputs of another to function. So this could be like a water treatment plant requiring power in order to perform its treatment, and then also for pump stations and other services that require power. And then the second is this idea of geographic interdependencies, where two or more components of the same geographical area may fail together. So this is the idea that if you have all your assets located in a single spot, if you have some sort of attack on that location, you can take out multiple parts of your infrastructure, either within the same network or across multiple networks at one time. So we want to capture that as well. And so we're going to model both of these types of interdependencies within this Bayesian network framework. All right, so I wanted to show, also talk a little bit about the data needs that are needed for these, to build these models. And so we needed data on system components, locations, and connectivity to build this model. And so we were looking at specifically at water facilities, distribution pipelines, and then connections with power and communications, which includes treatment facilities, pump stations, and other types of assets that require power and communications. And so for the service provision interdependencies, specifically for this example, then we're looking at power substations at each supply node for the water system. And these power stations, usually at a water supply node, there could be one or multiple feeds, so we wanted to capture that. That introduces, if you have multiple feeds, that introduces some redundancy that we want to be able to capture. And then there's also backup generators at some supply nodes. And so we didn't just want to say this specific water node needs power, but we can also get into more detail about how reliable is that power source as well. And so including both multiple feeds and also backup generators. And then for geographic interdependencies, we wanted to look at different service areas over the city. So we separated the water distribution components into different service areas at each and around each water supply component. So this is the idea that for a distribution network, each distribution node services a certain area, provides some level of service, and so we can split up the components into those service areas. So next, what we wanted to do was to actually test this model with historical data from a power outage event. And so I think this is really important. We could build all the models we want, but how do we know if they work well? Is there a question? Yeah.
So maybe you'll get to this later, so I'm happy to defer. Can you give me a sense of the scope or scale of the output of 1B? So how many nodes?
I have it. I have it on the slide. Yeah, number of nodes and links. Yeah. So for validation, I think it's really important we can build all the models we want, but we really want to be able to test it with some real data to make sure that what we're getting is correct. And so we're able to get data on a specific event that happened in April 2016, where there were storms that led to a power surge and an outage at a large pumping station, which then led to loss of pressure in drinking water for a downtown area. So we used the initial outage information to test the ability of the model from 1B to capture the effects of one system on another, so effects of power on water, and then also information on restoration of water supply to test how these systems can be brought back online quickly. And right now, so we're thinking about cyber attack for water. So water is susceptible to cyber attack in a few different ways. This specific threat we're looking right now is thinking about a cyber attack on the power grid that then cascades down into impacts on the water system. And so the purpose of this step is to make sure that we have a good model for these subsequent analyses. And so the next step that we want to do is to be able to visualize these interdependency impacts. So here is where I'm going to show the specific nodes and the number of links that we have. So we looked at pipes that were 18 inches and greater for Atlanta's water distribution system. So here's a graph of the supply nodes as the triangles, distribution nodes as those blue circles. So this is 112 components. So there's 7 supply stations, which includes pump stations and treatment plants, 105 what we call transshipment and distribution nodes. So this is where it goes from supply to more distributed supply of water, and then there's 244 links that connect all of these things together. So of course, this is kind of a decision we made as to what level of granularity you want to look at. You can go kind of broader out into looking at more regional, and then you might want to maybe do larger pipes, and then you could go more specific at a specific area. For example, like looking specifically at the downtown area, going down to pipes of 4 inches, 6 inches, but then that adds complexity to your model. So it's kind of a decision that we made in terms of kind of this idea of multi-scale modeling, and this is the scale that we looked at, so we could look at across the entire city and still have kind of a computationally tractable model. And so here for our validation, so we had a failed substation and then wanted to make sure that it would propagate through to the failure of these downtown nodes, and took some kind of tweaking and building of the model to get this validated model to work. And so with this, we can, by this visualization, we want to visualize to kind of enable end users, stakeholders to both be able to visualize the points of contact between systems, and then we can also run the model over time for dynamic visualizations. We could run different what-if scenarios. If different nodes in the network fail, how does that propagate through the network? And then if you observe some events, what are the potential causes for those events? So the next step, now that we have this kind of tested model that we can work with, we wanted to perform risk analyses under this threat. So we're looking again at a cyber attack on a power grid. And I'll show, as part of the outputs and deliverables, some of the results of these. But we wanted to be able, we have now the ability to predict outcomes and impacts of any sort of future attack with different assets targeted, different locations, different severities of locations. Essentially, you just change the state of one of those nodes in your network, and then it'll propagate through the entire network to show the effects. And this enables us to do these more comprehensive risk analyses to assess system vulnerabilities, including these interdependent effects. And then one of the key outcomes that we want from this is to identify critical assets for recommendation of risk mitigation strategies. And so we can perform these analyses and identify the ones that are most critical, that have the biggest effects. And then with that, be able to then, in part 3B, to integrate into ongoing City of Atlanta risk assessments. So this is really the implementation part of things. So we can run these risk assessments, and then we want to integrate the results of these analyses into what the city is already doing. So the first, Maximo MMS is their asset management system, and so they do these risk ratings of different assets that they have. And so we've been talking with them about integrating the results of our analyses and having different probabilities of failure, for example, for different assets, integrating that into how they assess the risk of certain assets within their network. And then they're also going through a certification process, looking at their risk profile to different types of threats. And so we've also been talking with them about how to best integrate the results of these kind of interdependent system analyses into those ongoing risk assessments. One thing that has come up in our discussions is this idea of integrating risks from interdependencies into a risk assessment for a single system. So typically for a water network, for example, you just consider the risks from within your network. But then we've been talking about, well, how do you incorporate then risks that come from cascading risks from power or from cyber attacks on the power that then trickle down and cascade to your system. So how do you kind of actually integrate that into a risk assessment for your own system? And then potential risk mitigation strategies that we've talked about are at the component level to add more backup generators, to add additional storage, and then also at the system level to build additional connections across. This is a little bit more difficult in terms of actual implementation, in terms of being able to build in redundancies and additional paths between different points of the network. And then one other big initiative that I've been working on that I think is a great opportunity for CIRI to really go from research into practice is Atlanta was recently selected as one of the 100 resilient cities through the Rockefeller Foundation, and I'm actually leading the initiative on strengthening and maintaining infrastructure for as part of the 100 Resilient Cities strategic plan. And so we've been talking a lot about how maybe this is an opportunity to work kind of across sectors, look across the city, and integrate kind of more comprehensive risk assessments into assessment of resilience. And then also, if you needed investments for resilience, this is kind of a way that you could point to an initiative that we're looking at these more comprehensive risks, and then a way to funnel investment into those types of investments. All right, so now I want to talk specifically about their outputs and deliverables. So I actually went not the direction of publications and conferences, but actually the models and the results of the risk analysis. So the first main output is this tested Bayesian network interdependent system model. So here is a schematic of how it looks. So on that slide with the X's as the nodes, now these are the specific nodes where the top nodes here represent different hazards. These could represent different threats, which is really how we capture our geographic interdependency. On this next line here, we have different power nodes. So these are our service provision interdependency nodes. On the next two levels, we have water supply and water distribution nodes. And then on this next level here, we have water minimum link set. So this is a way to kind of map how water flows through the network, how many different redundant paths you have. It's a way to kind of count how reliable your system is. And then at this final level here, we have different zones that we've split up for different service areas for inference. So you can see it's definitely like a multi-level thing. You can go into different levels of granularity at each of these levels to add complexity or more detail into your model. But it's a way to kind of propagate down these ideas of interdependencies into then, at the very bottom level, what level of service can you provide for your specific area that you're looking at. And then the results from a set of risk assessments is our second main output and deliverable using this tested model. So as I mentioned before, we want to be able to identify critical components and to be able to prioritize these components in terms of an impact on risk. And so one example that we started with is for critical components, we could have maybe 3 states. We have a red as inspect components as soon as possible, yellow inspect components in the next year, red is just kind of inspect components as scheduled. You don't need to do anything particular. This is about inspection, but we could also think about that these things need to be retrofitted sooner, or these things need to be highest priority to build in backups or redundancies as well. So not necessarily just inspection, but any sort of kind of discretized way of saying like really important, less important, and maybe things can go on as scheduled. So this is the results from one of our sets of risk assessments. So we have the green nodes, the red nodes, and the yellow nodes distributed across the network as one potential way to say, so this is going to be the importance of each of these individual nodes on the overall risk of the system, being able to provide water across the network. You could also focus on different service areas to say what's the probability of being able to provide water at downtown or at the airport. One of the of the 7 supply nodes, one of them is actually just services the airport, so we could also focus potentially on that as well. But the key is to have this tested model now. Now that we have it, we can really play with it however we want. And it's really in talking with we're hopefully going to meet with the city soon to kind of share some of the initial results and then also find out more about what types of risks they're particularly interested in. And so this really helps us define these critical areas to focus on for network resilience assessments, and also where to focus investment to increase resilience of the overall network. So now I wanted to switch gears a little bit to talk about our specific end user customers. So this is starting from Georgia Tech, that we have now the Office of Emergency Preparedness. And so we've been working really closely with Rhea Aiken, who's the Director of Emergency Preparedness there. And then the Department of Watershed Management, we started with the commissioner, and then specific, we're really looking at these interdependencies. So we've talked specifically with electrician supervisors and then managers of plants, but then also kind of, so it's really this, even within watershed, you go from individual plant managers to kind of larger managers as well. A lot of it's about actually like education about interdependencies and kind of making the case of it's important to think a little bit more broadly about your system and the potential vulnerabilities that your connections introduce and how that might change over time. And then with Atlanta Information Management, we started with the city CIO, Samir, and then we've been working also with these people listed here. So this is a lot of people involved in information security. So if we are collecting data, like monitoring data, for example, how do we integrate that into our risk assessments? And so information security is a big part of that. And then I wanted for these specific groups to talk about the specific benefits to end user customers. So for the Office of Emergency Preparedness, this is really to enable the city to work across these silos and map infrastructure systems that are relevant to city emergency preparedness and response, including the interdependencies between these systems. And so the Office of Emergency Preparedness is actually a great office for that because it looks at the city at a little bit of a larger scale rather than at specific individual systems. And then for Watershed, the big benefit is to be able to identify critical components in the system based off of interdependencies and vulnerabilities that are introduced from connections with other networks, including power infrastructure and cyber vulnerabilities that they might not be able to assess with existing tools and methods. And then for AIM, it's to see and understand the impacts of connected infrastructures on system performance based off of monitoring data and these interdependent systems effects. And so AIM does a lot of work with this distributed monitoring idea and how do you kind of integrate these real-time information. And so that's something else that we're also looking at is how to integrate kind of real-time updating information into our model. One of the good things about the Bayesian network model is that you have this immediate updating. If you update the state at one node, you can propagate that through immediately to see the effects across the network. And finally, in terms of the deliverables, the benefits for this tested Bayesian network interdependent system model is this ability to predict outcomes and impacts under these different threat scenarios. We can change the types of assets targeted, locations, severities of occurrence. And then for the deliverable of the results of the set of risk assessments using the tested model, the benefit is to be able to provide recommendations for investment, to decrease system vulnerabilities and increase resilience, and for all of this to be accounting for interdependent system impacts when we're doing that. And then just as to go back to what our initial goal, our overall objective is to enable municipalities to better understand their vulnerabilities and make informed decisions based off of comprehensive risk assessments. And so with that, I wanted to give a few references here of where you can find some of this work and then have my contact information here, and I'm happy to take any questions that you might have. Thank you very much. Yes.
So I know maybe go back to that scheduling graph you have.
Sure.
Color-coded scheduling graph.
Yeah.
So the question I have is, given the scale of what you're looking at, what about this scheduling graph was surprising to you?
Yeah. So it was interesting because I think there's like a cluster of ones that are more densely connected, and then there's also ones that are more remote. So I think it's interesting to think about the vulnerabilities that the different types of topology in a network introduce, because you can think of a remote node being vulnerable because it doesn't have a lot of redundancies and it doesn't have a lot of options if whatever it's applying it goes down. But then at the same time, for a kind of more densely connected part of the network, you might have more redundancies and more kind of ability to recover if different supplies to those specific nodes fail, but then at the same time, if one of those fail, it also has more effects on the nodes around it. So I think that was kind of an interesting observation.
Yeah, sure. So I guess my point is there's this version of the model that has nothing to do with interdependency. It's just the water model.
Sure, yeah.
And this is going to look like some cross product of the topology, as you just suggested, right. and what could fail there. Maybe there's a pump at this location and a sensor in another location.
Yeah.
But what's the difference between a risk assessment that looks exclusively at the water topology
sure.
and says, I'm going to kill this, let's say a physical attack, I'm going to walk and blow something up, what should I go blow up?
Sure.
Versus what the risk assessment looks like when you combine it with the interdependency of the IT infrastructure, sure. and how do those two things change?
Yeah, so I think it's a good question because it's kind of you have the initial level where it's just the water, and then you're going one level up, and we're trying to look now at the power and communications and its effects. And so I think it's a few things. So first, looking at the specific nodes that do require power and communications, and then it's the ability, now we want to see, like, if we add specific backup generators at these specific nodes, how does that propagate through? So not just the reliability of the node itself, but the reliability of the things that are supplying that node, if that makes sense.
Yep.
So yeah, so to be able to look, I guess one level up is the benefit or the advancement beyond just looking at a single, because we might be able to, with just the water system, to say, okay, this is my most critical treatment plant. but then maybe that particular treatment plant has a lot of backups, it has a lot of redundant feeds, has multiple feeds from substations, and it has backup generators, and then you might say, okay, well, that one's actually probably okay, even though that was, just looking at the water system, the most critical one, but then maybe you have another pumping station, which if you just looked at the water system network, you wouldn't say that that's that important, but then when you account for then the communications and the power, it becomes like a more critical.
Yeah, and you don't have this yet because you haven't gone back to them with your schedule, but
Yeah, so-
I'd be crazy interested in hearing them say, oh, here's what our schedule is now, and here's the changes to the schedule you're doing. And if you could explain to them in a way about this interdependency that says, hey, no, you really want to schedule this instead,
Right.
I think that's going to be very compelling for the looking at both of these things together.
Absolutely, yeah, I completely agree, yeah.
Great, okay.
Thank you.
Very much.
Clap it up.